This afternoon, we're going to be talking about maximizing HVAC efficiency, flexibility, and resiliency with very high efficiency dedicated outdoor air systems. Again, my name is Jordan Pratt. I'm a senior engineer with Energy 350. I'm presenting today on behalf of the Northwest Energy Efficiency Alliance, or NEA. NEA is a nonprofit organization that focuses on energy efficiency. They are funded by the Northwest Utilities, so there's over 140 of them. You'll see a few over here that you probably recognize: Puget Sound Energy, Seattle City Light, Snohomish PUD, Tacoma, some other ones in your guys' area. NEA really works on market transformation. They kind of work in the background. So they might work primarily with equipment manufacturers, design engineers, architects, and they help provide trainings and financial support to try to get the most energy efficiency technologies to the market and to have them be adopted by designers, contractors, and the such. And so they do a lot of field testing and midstream incentives. I work for a company called Energy 350 out of Portland, Oregon. We're energy efficiency engineers. We work primarily for the utilities and nonprofits on energy efficiency program delivery and research. I work mostly with NEA on kind of the research and development of new technologies as well as systems. Today, we'll talk about why high performance HVAC matters, what is the very high efficiency dedicated outdoor air system concept, some results from 14 demonstration projects that we have been partnering with NEA as a part of over the last 6 years, some comparisons with the Washington State Energy Code 2021 commercial version, and then a few local case studies. First, let's talk about the why. So why HVAC matters. HVAC matters, as most of you know, because it uses a lot of energy. Commercial buildings consume over half of their total energy in their heating, ventilation, and cooling systems. Cooling gets a lot of focus in commercial applications, but the energy pie chart shows that space heating is far more important, especially in heating dominant climates like the Northwest. Ventilation is a big part of it as well. When you look at how much fan energy, heating and cooling energy we spend on conditioning and delivering ventilation air to dilute indoor air pollutants, it's significant, and on average more than even the cooling energy in commercial buildings. When you break that down by building type, when we look at offices, retail, and schools, which will be the primary focus based off of DOAS technology being a really good fit there, it's even more significant. So space conditioning in office buildings is closer to 60%. Schools, it's about 58% of total energy use, and in retail, it's about 54%. So that heating, cooling, and ventilation is a big part of overall energy use in commercial buildings. All right, what is very high efficiency DOAS? I'm sure many of you, if not all of you, know what DOAS is. We'll be talking about a high performance version of that. What is it? It's a proven system approach to high performance HVAC. So when I say proven, we have been intimately involved in over 14 demonstration projects since 2015. On average, those systems saved 69% of HVAC energy use and almost half of the total building's energy use. Our experience has been that they also provide extremely good indoor air quality, enhanced thermal comfort, and just an overall reliable and robust design. Quick schematic. When I talk about DOAS and very high efficiency DOAS, we're talking about an entire system. So not just the ventilation unit, we're talking about kind of 4 key concepts that make a DOAS system very high efficiency. One is a fully decoupled system. So we have equipment or a few pieces of equipment that are dedicated to providing ventilation air, and they do so typically directly to the building. And if not, at least downstream of the fan coil units. They do that in a very high efficiency application. with a heat recovery or energy recovery ventilator that delivers at least 82% sensible effectiveness. We find that to be extremely important, especially in climate zone 4, so kind of the coastal marine climates, because typically we can drastically simplify a system when we get to this level. We can deliver ventilation directly to the space year round without any supplemental heating or cooling, as long as you follow some kind of proven design strategies. You can do this without duct heaters. That heat recovery or energy recovery ventilator can deliver room neutral air essentially year round. And then on the primary heating and cooling, the comfort conditioning system, we recommend a very high efficiency electric heat pump system. We have a set of minimum efficiency guidelines. That's essentially the top order of electric equipment on the market. This aligns pretty well with Energy Star ratings where applicable, which typically means it ends up being an inverter-driven heat pump technology, usually a VRF. Mini splits can also be done with air-to-water heat pumps, ground source heat pumps, heat recovery chillers, and a few other kind of larger chilled water, hot water plant systems. And then another a concept that we find oftentimes gets ignored or purposely overlooked in commercial applications. It's right sizing the heating and cooling system. So using load calculations that correctly deduct the amount of ventilation load that's been eliminated by a passive heat recovery, energy recovery ventilator, and then without significantly using safety factors and using good diversity and correct assumptions. We found time and time again that systems are oftentimes installed far more capacity than they need to be. And this not only costs more equipment, it's more expensive to maintain, and it usually operates significantly less efficiently when it's oversized. As I mentioned, there's 14 demonstration projects and growing that we've been involved with. So a large number of offices, schools, restaurants, and a dormitory and a couple other small offices throughout Oregon, Washington, Idaho, and Montana. Most of these systems have been smaller. We found that this approach works really well in offices and schools between 5 and roughly 50,000 square feet. This is the energy use intensity before and after the conversions of these 14 projects. One thing you'll notice is that commercial buildings are all over the place in terms of where they start. We have starting EUIs everywhere from 20 all the way up to 120, and these are similar climates and similar applications. And so there's a lot of variability within commercial building energy use. On average, these projects I mentioned saved 69%. So we had a building EOI before conversion on average of around 65, and they finished around 34. What's amazing about all those different starting EOIs was the ending EOI. So this system really has shown to be quite consistent is where you're going. So on average, the HVAC energy use intensity after converting to very high efficiency DOAS, it was 11.4 kBU2s per square foot per year on quite a tight band of these buildings. We threw out some of the colder climates since they're a little higher naturally with more extreme climates, but this is all buildings kind of on the I-5 corridor, Portland, Seattle, everything basically west of the Cascade Mountain Range. Offices and schools kind of didn't matter where they started, but they all finished at a very low energy use. Outside of just the energy use, these systems, we measured a number of different indoor air quality metrics. We followed the thermal comfort from the occupant standpoint very closely. We did a lot of surveys before and after, post-occupancy surveys. And what we found is that the indoor air quality from these systems improved greatly. The indoor or the occupant thermal comfort was far superior to the previous systems, which are typically either packaged gas rooftop units or VAV with reheat, was by far the most common. And then these systems, being all electric, ultra low EUI systems helped significantly decrease their carbon footprint. So very important to some of the owners and building owners in terms of their sustainability goals. Touched on this, but the applications that this works really well in our experience has been small to medium size buildings, so typically less than 50,000 square feet. Works great in new construction when you have a blank slate, but also all of these, in fact, were either major renovations or just HVAC conversions. Schools, offices, government, retail, and multifamily. It's kind of been the sweet spot. Certainly can be in other applications, but these are the ones that we've found to make the most sense. All right, keep moving here. Let's do some comparison to the 2021 Commercial Washington State Energy Code. How does this approach compare? So first, definition and applicability. So section 4.3.3.5 for buildings with occupancies as shown in this table, outdoor air shall be provided to each occupied space with a DOAS, which delivers 100% outside air without requiring operation of the heating and cooling system fans for ventilation air delivery. That table basically includes almost all assembly occupancy types, businesses, which is of course includes offices, professional services, notably excludes restaurants, labs, and food processing. All educational schools under 12th grade, so not including higher ed. And then the M group, which is mercantile, includes retail, markets, department stores, etc. So this is a lot. This is a significant portion of all buildings that we think of as commercial buildings. So basically in all of these, in new construction and major renovations or major HVAC changes, DOAS is required. This was also required as of the 2018 version, but there has been a few notable changes in 2021 version. The exception are mechanically ventilated spaces, are still able to avoid being the DOAS, and then high efficiency VAV exceptions complying with C403.6.10 is also a notable exception. How does this compare to NEA's kind of guidance, their advanced guidance on very high efficiency DOAS? In general, they're very similar. Not being a code, NEA's is more of an advanced design guide. We're generally, recommending this for any commercial building outside of restaurants, less than 50,000 square feet. So similar in definition and application. In fact, NEA has been very involved in the code development cycle over the last 7 or 8 years. Next section is energy recovery, ventilation, which is required in those building types. Very high efficiency DOAS, I mentioned, recommends 82% sensible effectiveness. Washington State Energy Code, as of 2021, now requires a 60% total enthalpy or 68% sensible. So a little bit lower than the VHE DOAS, but there is in the energy efficiency credits section, which is also required in new construction and major retrofits. I'll get into that a little more detail. It has an 80% for the high performance DOAS option. So very similar for the advanced energy package. So what is that? All buildings above, all new construction buildings greater than 5,000 square feet, or any that are having major HVAC system changes or a change in occupancy are required to meet the energy measure credits listed in table C406.1. Here's a snippet from that table. So Group B businesses are required to have 42 additional energy measure credits. Schools are required to have 48 additional efficiency credits, and retail at 74. I mentioned this high performance DOAS package. This gets you basically half of the way there with businesses, I think 80% of the way there with schools, and more than half of the way there with retail as well. So this high performance DOAS measure is significant. It gets a huge chunk of the required efficiency credits. What are all those requirements? It's all the basic requirements of C403.3.5. That's the DOAS section. But it adds, as I mentioned, 80% sensible effectiveness instead of 68. Requires economizing. So this is just bypassing the wheel or heat exchanger between 55 and 75 to provide airside economizing. And then a little bit more strict fan power. So less than 0.769 watts per CFM or greater than 1.3 CFM per watt. How does that fan energy compare to VHE DOAS? We have landed on 1.3 CFM per watt as being the minimum fan efficacy. The base code says that you shall not exceed 1 watt per CFM or 1 CFM per watt. It can't be, or it has to be more than 1 CFM per watt. And again, this high performance DOAS is a little bit better, 1.3 CFM per watt, which aligns exactly with very high efficiency DOAS requirements. All right, primary conditioning system efficiency. As I mentioned, the VHE DOAS approach requires kind of that upper quarter of equipment, heat pump equipment that's on the market. So it aligns with Energy Star minimum where applicable. So one example of this in like a typical 10 to 20 ton VRF compressor unit, which even larger systems often use 20 ton modules, requires a COP of 3.25 at 47 ambient or 2.07 COP at low. This is quite a bit higher than the not quite a bit higher. It's a little bit higher on the heating side of 3.2, but on the cooling side with an IER of 18, it's significantly higher. So the VHE DOAS is a little bit more strict in terms of these efficiency requirements. Most of these are fairly easily attainable using, I mentioned those inverter driven, so variable speed heat pump technologies. Many of the major manufacturers can meet these levels, so they're not that difficult to meet with that type of equipment. And then decoupling. So how is ventilation air delivered to the space? This is Washington State Energy Code. The DOAS supplier shall be delivered directly to the occupied space or downstream of the terminal heating or cooling units, exceptions, chilled beams, sensible only cooling units with pressure independent airflow, and terminal heating and cooling units that comply with the low fan power. You can see from the Energy Code standpoint, the main reason why they do this is they want terminal units fans to shut off when there is not a call for heating or cooling. So that's kind of the idea of a decoupled system, is they can operate independently of each other. When there is no call for heating and cooling system can shut down while still providing ventilation air to the space. Likewise, when there's no occupants in the space and we don't need the same levels of ventilation that we do during occupied hours, ventilation air can be turned down or off, and the heating and cooling system can still operate to maintain space temperature when needed, or just to prevent overheating or freeze protection. Our experience is that that's actually a pretty small reason why to do it. Even more impactful is, on the ventilation air, just having a lot of flexibility to ramp ventilation air up, to do flushes in terms of kind of indoor air quality before or after, to be able to optimize control of each space, not just to be able to shut them off, but to be able to kind of dial in each system to be able to control to the function that they're designed for. One example of that is we've had a couple demonstration projects, not included in those 14, but kind of research studies where we've had partial coupling. So ventilation air delivered to the return side is a very common strategy, especially in Oregon and other states outside of Washington. do this because you don't need nearly as high of ventilation or heat recovery effectiveness, or you don't need as much post conditioning if you have a heating or cooling coil on your DOAS units. But this can cause some significant issues, and we've proven this in a few different projects where indoor air quality suffer. Here's an example of that. This is a typical office building with kind of a partially coupled design. So VRF fan coil units are the primary heating and cooling system. So when the ventilation air is delivered on the return side, this works fine when there's an active call for heating or cooling. This is the fan coil unit power. So it's cold in the morning. Fan coil unit is cycling on. CO2 remains low in the space. Then we start to have the temperature warm up, and it's like a 50 degree, 55 degree day. And so there's no calls for heating or cooling for quite a while as people in the office, and CO2 spikes in the space. And this is because the ventilation air is not being delivered to many of kind of the end of the run offices. So this is a fan coil unit that's serving like 9 offices, and the furthest offices away are oftentimes starved for ventilation on these mild days. So this happened, throughout the spring and fall season in this particular office, and we've seen this in basically every partially decoupled design we've seen. So we feel that fully decoupling, delivering ventilation air directly to the conditioned space is a far better approach for ensuring that ventilation air gets delivered consistently during occupied hours. Here's another example, and this, kind of aligns with the energy code's goals of low fan energy. But this is two systems. So the blue triangles is the normalized average daily energy power consumption of the VRF system in a VHE DOAS system. So this is fully decoupled, followed all the design requirements to a T. And the orange circles are a system that is partially coupled. It's actually the same example from before. So this is a system when the VRF system was coupled with the ventilation air, and it was a far oversized system too, which we found to have a big impact on energy usage. One thing that really jumps out, I think, is that in kind of these mild temperatures, this VRF system that's not coupled and fully undersized, they're fully decoupled. So they're able to completely shut off when there's not a call for heating or cooling. They don't continue to run. It's almost nothing. It's less than the ERV fan energy. This coupled oversized system uses a ton of energy, even in very mild days. The reason why I'm comparing these buildings is these buildings are right next to each other, same occupancy type, in the same place, very, very similar buildings, and also almost exactly the same equipment, same efficiency, high efficiency equipment in both situations, but basically 3 times the energy use from not following a couple of the key design requirements, or design principles rather. All right, we'll move on to some results from a few Northwest projects. We've got many case studies. All of them are on the Better Bricks website, along with the design guides and some of the system research that we've done. But here's a couple highlights. So this is a Seattle office building, or rather one floor of a 5-story building. This is a tenant improvement that they had existing a VAV with electric reheat. It's around a 15-16 ton building or HVAC system. Pre-conversions EUI was 51 kBTUs per square foot per year. New building EUI was 29. So we had a 69% reduction in HVAC energy, so right on average with other buildings in the region, and a 42% reduction in building energy. System did that with a 14-ton VRF system and 1,000 CFM HRV. Other big result of this that utilities care a lot about, and I think that building owners should care about too, because it's going to start being a significant part of their energy bill, will be demand costs. But the change in peak winter demand was a 30 kW reduction. So the coldest 15 minutes of the month, The conversion system used 30 kW less. That's pretty significant for this little, 6,000 square feet of office space. Likewise, about a 6 kW reduction in peak summer demand. Another example, office building in Portland. Intimately familiar with this building. This is Energy 350 office. And so, as you can imagine, we have many, many sensors and have been studying this for the last 3 years. So we have a lot of data on the system. We had, before conversion, 2 constant volume packaged gas rooftop units and 1 small split system heat pump for a conference room. This was about 28 tons of heating and 20 tons of cooling capacity. We replaced that system with a 2,000 CFM heat recovery ventilators and 1 10-ton VRF system. So I mentioned the right sizing. This is not a unique example. We had almost half of the buildings that in our demonstration projects, when they converted to very high efficiency DOAS, were able to cut their system capacity in half. So 20 tons of cooling down to 10 tons of cooling. Obviously, this previous building was significantly oversized, but by eliminating most of the ventilation load with this heat recovery ventilators, and by switching to a zonal heating and cooling system instead of a single zone system, we were able to significantly reduce the capacity of the system. From an energy standpoint, savings were drastic. 84% reduction in HVAC energy use, 79% reduction in our building energy use. So ultra low EUI. No other measures outside of HVAC were done to get here. This is old converted warehouse with uninsulated brick walls and single pane windows. So it's not like this is this fully modern ultra low energy building other than the HVAC system and the way it's controlled. So pretty significant results with just an HVAC upgrade. Yeah, just more on the sizing. Here's the 2 packaged gas rooftop units replaced with 2,000 CFM ventilators on roof conversion curbs. So we were able to utilize the existing curbs with just curb adapters. Very straightforward. We used a local contractor that did a great job, but just somebody who's doing rooftop conversions all day had no problem with this installation. Very straightforward conversion from a constant volume package units to this very high efficiency DOAS concept. But again, 20 tons down to 10 tons, so cut the system capacity in half. System got tested. We hit 112. We had that heat dome effect that very summer. Building crushed it, even at cutting the system capacity in half. And this outside air temperatures being 20 degrees over our design cooling condition, still we're able to maintain a comfortable space temperature. And this is, people often run their HVAC units 24/7 in extreme conditions. We didn't. We shut it off. We wanted to see if we left it on a typical schedule, if it would still be able to catch up, and it was, with that ventilation load being basically eliminated with the heat recovery, 84% sensible heat rejection. That's played a big part of that. It kind of insulates you a little bit from extreme conditions. So there's just a lot of resilience that you bring in when you have this super high efficiency passive heating, heat rejection or heat recovery in the winter. Yeah, I just want to reiterate those 4 key concepts of this very high efficiency DOAS design. So again, 1, ventilation system is fully decoupled or fully separated from the heating and cooling equipment. 2, very high efficiency heat or energy recovery ventilator. 3, a high performance electric heat pump system for the primary heating and cooling system. And 4, is right sizing the heating and cooling equipment to accurately account for the reduction in ventilation load that heat recovery ventilator provides, and yeah, right sizing equipment, selecting the right tool for the job. All right. Yeah, I mentioned this, but the Better Bricks website is NEA's market-facing website. So we really see this as a really useful research for designers, for building owners, for anybody who's involved with commercial HVAC design. So we have all these case studies that I mentioned today, and many other case studies as well. Some really interesting pilot reports, so the pilot projects that we first kind of kicked off the system that we've learned a lot from over the years. Some kind of detailed energy savings, as well as some of the modeling that we did. So design requirements and guidelines. So as I mentioned, to see this is kind of an advanced energy design guide for how to do or how to design an ultra high efficiency HVAC system, and kind of what we recommend and why, what kind of benefits each different design decision has. We maintain a qualifying list of energy recovery and heat recovery ventilators that has that very high level of sensible effectiveness, as well as really efficient fans. There's also a few other kind of aspects of that kind of requirements that we have that I didn't touch on today. We like to see ultra low cross-flow leakage. We also like to see efficient defrost control, which can pop up when you're recovering, recovering very cold conditions at a very high recovery rate. And then we also have a few other requirements just on insulation and control strategies, kind of some best practices. And so we maintain a list of compliant products. When we first started these demonstration projects, there was very few ERVs and HRVs that met these requirements, but that list has expanded, and there's currently over 6 manufacturers and over 100 different products that can meet these requirements. So they're out there. There's some very good products. And then, there's also some really good research in terms of the value proposition and economics, and some indoor air quality studies as well. There's some CFD analysis that was done through University of Oregon. So a lot of really cool research is on the site. So definitely, if you're interested in this and want to see more of what NEA has been up to, I encourage you to go to thisbetterbricks.com. And just, search for very high efficiency DOAS. All right. With that, I think I saw some questions pop up. So I'm going to start trying to work through those if I can find the chat. Let's see here. All right. Okay, I got a question from Dan O'Neill. How are you dealing with very small ventilation CFM to the small office space? Most tab contractors don't like balancing at less than 50 CFM. So that's a great question, Dan. So that's something that we have to basically hold our tab contractors or the mechanical subcontractor who's managing them. We have to hold them to it, and we have to say, hey, this is very important. We have a lot of spaces with really low ventilation. And so there are equipment, there are hoods, powered ventilation hoods or powered flow hoods that can measure down to 10 CFM with a pretty low error. So that's what we basically required them to do, is say, hey, you need to have a powered ventilation hood. We actually have one in our office, so occasionally in some of these sites where a contractor has not had one of those pieces of equipment, we've kind of shared them, and this is part of the training the market that NEA needs to do in emerging technologies. So yeah, that's a great point. It's something that's got to be specified, and you got to hold them to it. Yeah. Let's see. I'll open it up for any more questions. So if you got any more questions, throw it in the chat, or if you can unmute yourself, I'm happy to take questions live as well.
Well, on behalf of our chapter, if there are no more questions, I see that there's a link to an upcoming event in the chat. We'll also share that. And actually, there are a couple more questions, Jordan. How did you decide on 82% efficient from Stefan Forner?
Great question. So the 82%, effectiveness that we've landed on. It was based on quite a bit of research and primarily on the simplification of the system type. So in climate zone 4, where NEA is very focused on, just with most of the major population centers in this climate zone, that 82% level at kind of a design winter condition of like 27, 28 degrees will allow the system without any post conditioning to deliver ventilation air at like 62, 63 degrees. And most of the literature we found has shown that when at ultra low velocities with well-placed diffusers, that limits thermal comfort issues in the winter. That's really what it comes down to, is on the winter side. So that 82% was a level with a little bit of buffer zone that allows no post conditioning and still delivering relatively room neutral air. So in warmer climates, you could certainly get away with a little bit less efficiency, but we're seeing that a lot of units are being able to deliver that with kind of the right heat exchangers. I forgot to mention this, but the technologies that allow that super high efficiency are really limited to a few different heat exchanger strategies. One of them is a wheel, an enthalpy wheel that's got a large level of surface area. So there's a few wheels out there that do this really well. Another one is a counterflow heat exchanger. So there's a couple counterflow plate style, so plate and frame style heat exchangers that have like essentially micro channels, and so they really maximize the amount of time in which the exhaust air and the supply air kind of interact. So yeah, counterflow. And then the last one is there's one dual core reciprocating device where essentially it reverses the flow through two different aluminum heat exchanger cores, and that one is shown to be very effective in especially extreme cold environments. Good question. On the colder climates, would the efficiency be higher? Colder climates, there's not a lot of equipment that'll do it even higher than that, and I think that there might be some diminishing returns in terms of how much the technology costs to manufacture. And so typically what we'll see in the colder climates is that 82% or maybe a little bit higher is good enough with just a well-controlled post-conditioning coil. So as long as you're not using that post coil to deliver 80, 100 degree air, and you're just doing it to kind of top it off, even in climate zone 6, so in like the coldest parts of Montana, it ends up being not a ton of energy as long as you're controlling that well. All right, had some questions on economics. So yeah, Natasha asked a question on general cost and how that compares to other system options. This is a difficult question to generalize, and one that the goalposts are moving so quickly that anything I say is certainly wrong. But what I can speak to is those 14 demonstration projects, which are roughly from 2015 to about 2022. We saw system cost ranging from about $12 per square foot up to about $35 per square foot. And of all the competing system quotes that we got, so we got some competing systems, that was actually like less costly than even kind of code minimum system types, outside of like just a like for like package rooftop unit swap. So any zonal heating and cooling system was the same or more. So this is actually a very cost competitive system. When I look at more recent data, as we're looking in like 2020 and beyond, the total system cost, in these kind of small to medium offices with pretty straightforward installations tend to be more like $30 to $35 per square foot. But again, from what I've seen and comparing that to like Washington state energy code systems, when you kind of right size that system and do things simply and efficiently, it ends up being almost no premium, if not even less expensive than a lot of code minimum DOAS designs. So there's a bit of kind of synergy between higher efficiency, like a little bit more premium on the ERV side, but allows you to downsize your primary heating and cooling system, simplify on the controls, also simplify on the amount of post heat and kind of the tempering on the ventilation air. So that, yeah, the incremental life cycle cost assessments have been very good when we've compared them to code minimum systems across the board. And this is, the caveat I will say is this is in like a full system replacement, and kind of comparing apples to apples. Nothing's quite as cheap as replacing a single rooftop unit with a single rooftop unit. So most of these numbers that I have are like, if you're going to a zonal heat pump system, incrementally doing it right and doing it with this very high efficiency DOAS concepts, like nearly instant, within a couple year paybacks oftentimes. All
There
right.
seems to be one more question about imbalanced outside air exhaust air due to separate exhaust streams, leaky facades such as kitchens and exfiltration. Recommendations for that situation?
Great question. A couple of the early pilot projects we had were very similar to this. Kitchens, restaurants, very leaky buildings. And to be honest, we really struggled. The contractors really struggled to get it right. And that has since led us to kind of stay away from restaurants, kitchens, areas where there's a lot of dirty exhaust that needs to be handled separately. And there's some danger fouling the heat exchangers. So in general, with that application, we actually don't recommend it, this super high efficiency DOAS option. I think there's better kind of systems that can handle that. But with the imbalanced exhaust, this is definitely something that we've run into. So exactly right. If you have kind of standalone exhaust, and this is leading to an imbalance in your exhaust air, in particular, if you have less exhaust air at your ERV, HRV than the ventilation air, this hurts your heat recovery ventilation. Generally, it doesn't have a huge impact as long as you're looking at like a 10% exhaust. So in those situations, one thing that we've done is we've kind of had those standalone exhaust systems tied in and on schedules. And so as much as possible, if we could run it at balanced ventilation, exhaust supply air, we did that. And so it wasn't taking nearly as much of a penalty. But yeah, sometimes it's unavoidable and you just have to take that penalty. And in that case, a little less efficient. You may need a post conditioning coil. So maybe a little duct heater of some kind. But again, like especially if that's controlled well, it's a very small impact. And actually, a couple of those demonstration projects did have that where they weren't comfortable delivering 60-degree air when it was very cold, and they had imbalanced exhaust air and supply air. And so they just said, okay, we're just going to have a little duct heater, but we're going to make sure that we only run it when ventilation air does fall below, I can't remember what exactly, below 62 degrees. And we're not going to deliver it at 80 or 100 degrees. We're only going to use enough post heat or mechanical heat to deliver it at 68 degrees. And then we're going to let the primary heating and cooling system, which is very efficient, handle a majority of the comfort conditioning. Does that answer your question? Okay, Megan?
Folks are muted, and she said yes.
Oh, cool.
Well, that's the end of our time here. I want to give some folks a little bit of time back for your lunch break. And thank you so much again, Jordan, for your presentation. We'll be posting the recording to the website here shortly. And as always, if you have any questions, you can email membership@pugetsoundashray.org, and we'll try to get back to you if there's specific questions we need to funnel to our speaker. So thanks, everyone, and have a good rest of your day.